Well, good evening, everybody. Welcome to the Open STEM Lab here at the Open University in Milton Keynes. I'm Dave Rothery. I'm the chair of S283, the Level 2 Planetary Science course, and I'm also the lead educator on the Moon's MOOC. With me is my colleague, Julia Semprich. Welcome, Julia.
Thank you.
I'll introduce Julia to you very shortly. Now, this is an event that we run for students on S283 and learners on the Moon's MOOC when that is running. That's a massive open online course that we run through FutureLearn. But we've invited the wider OU planetary science community as well. So whoever you are, welcome. Please use the widgets, which are, well, they're on the left of my screen to vote on various things and to tell us where you are. And we'll come back to those at the end. And also use the chat window to ask any live questions. The main purpose of this is to answer whatever you want to know about planetary science to the best of our ability. Now, we've had some questions in advance, which is great. We've got some prepared answers for those, but we'll be looking out for live questions as well. But before we get to that, we'll tell you a little bit about ourselves. So first of all, Julia, tell me and all the good listeners what you do and who you are.
Yes, I'm a research fellow at Astrobiology OU, and I'm actually not an astrobiologist, I'm a petrologist, and I study processes in the crust and upper mantle of planetary bodies, mostly terrestrial planetary bodies. And so, for example, I'm interested in the changes that happen in the mineralogy within the crust with depth and how that influences the density and the seismic velocity of the crust and the mantle. And this also has implications of the settings, like how thick could the crust be of planetary bodies and the tectonic regimes. I'm also interested in melting processes, which is particularly interesting for Venus because Venus is very hot and volcanically active, or very likely volcanically active. And I'm also studying fluid rock interactions on Mars. And in many of these scenarios, you probably know, it's very difficult to get data, so I use a lot of petrological computer modeling, but whenever I can, I also go out into the field and collect samples and try to get some analog data.
And you were away in Iceland like half of Astrobiology OU, it seems to me, last summer, weren't you?
Yes, Iceland is a fantastic country because it's a good analog for Mars, particularly Mars. It has a lot of basaltic rocks, and the Martian crust is mainly basaltic as well. Mm-hmm. Then it also is in a colder climate, and we know that the Mars climate nowadays is also very cold, and it also has hydrothermal activity, which may be both relevant for Mars, but also for some of the icy moons, because there's some hydrothermal activity going on. And so I actually recently, last year, was in Iceland, and I have brought some pictures from the field side. So here you can actually see some of the volcanic units in the foreground before the very gorgeous glacier. And this is a extinct volcano, central volcano, and it has been hydrothermally altered by hot fluids going through the whole system. And in the next picture, we can actually see some of these hydrothermal veins.
How long did you have to wait for that sunny day in Iceland?
It was actually gorgeous weather. It was amazing. We had almost all days in the field. We had nice weather. We had 2 days of a gale where we could not leave our cabin. Yeah. But all of the other days we were out there. There was just one day when we had rain. Absolutely lucky weather in Iceland.
So here are your hydrothermal veins.
Yeah, right? So here are my hydrothermal veins. And in this whole system, we have a lot of different hydrothermal veins. Some of them are these tiny, small ones. Then we have really huge ones. And I actually have brought a sample of one of the bigger ones. So we have the sample here. It is mostly calcite, and we can see the nice little calcite crystals in this one. And why are we so interested in hydrothermal systems? That's mostly because they could potentially harbor life on Mars, because they could provide temperatures and nutrients for microbial life in the subsurface for Mars.
Okay. And do organisms live inside these veins in Iceland?
Well, the problem is that because we are on Earth, there are organisms everywhere.
Yeah.
So that is actually not a very good measure. So and also I'm not a microbiologist, so I'm mostly interested in the higher temperatures, 150 degrees Celsius and upwards. But once these fluids cool down, they could potentially be habitable.
Yeah. Now, I've seen pictures of veins on Mars from Curiosity in particular, that rover, but those are mostly gypsum veins, I think, rather than carbonate veins, aren't they?
Yes. Mars has some carbonates, but in most cases, these are the veins that we see are gypsum and are lower temperatures, so relatively low surface temperatures, 20, maybe 50 degrees, but usually lower than that. So they form at lower conditions than this hydrothermal system that I'm talking about.
But they still need aqueous fluids.
They still need fluids to form, yes.
Thank you.
So, Dave, most of the viewers will know that you are involved in the Bepi-Colombo mission to Mercury. Do you have any updates?
Well, Bepi-Colombo is more than halfway through its cruise to Mercury now. It's already had 2 flybys of Mercury. It will get into orbit around Mercury in December 2025. And we're very busy here with PhD students making geological maps of Mercury. Got that wrong again. Behind me here is a geological map of Mercury, which has been made, this one's been made by some Italian colleagues, for 15 map sheets to cover the whole planet Mercury.
Wow.
And we're planning to get 7 of them completed here, not from Bepi-Colombo because we're not there, but with data from NASA's mission, which was Messenger. We're making our geological maps to set the context for our observations, and then all the maps will have to be done again because we'll have better data. We've had 2 flybys of Mercury on the way to get into orbit about Mercury. We've got several more flybys to come before we can be captured into orbit. And during cruise, we've got 2 spacecraft travelling together because we're taking a Japanese spacecraft with us and we've got a propulsion unit behind. So our science instruments, by and large, can't see the sky, but we have got some monitoring cameras on board. And I'll just show you one picture from last year's flyby. There we go. There's bits of spacecraft in the foreground, bits of a magnetometer boom and an antenna. But you can see Mercury in the background. And that's not really a science image, it's just a 1024 by 1024 black and white webcam. But there's some nice features there. There's an escarpment catching the sunlight in the lower part of that image. And we knew we were going to see that well when we flew by, and it hadn't got a name. So we said to the International Astronomical Union, we're going to see this escarpment really nicely. You know, can you give it a name? Because slowly the features on Mercury are being named. So they called it Challenger Rupes. Rupes is the descriptor term, just meaning scarp. And Challenger is after HMS Challenger, a British ship which mapped the floors of the world's oceans in the 1870s. It's a very famous expedition, the Challenger expedition. I didn't ask them to name it after a British ship, but that was quite neat that we had Challenger Rupes, so I was pleased about that. And it's a fault scarp that we don't understand. It doesn't fit in with the general pattern. It's a fascinating planet, Mercury. Tectonic activity, lots of volcanoes. We'll learn a lot more when we get there.
I'm excited to hear more about that.
Yeah.
Also, I heard that you were flying by Venus.
We had 2 Venus flybys as gravity assist manoeuvres, but magnetometers were working, charged particle instruments. We learned a bit about the bow shock of Venus as it deflects the solar wind. It wasn't designed to do science at Venus. We didn't find any phosphine, before you ask.
I wasn't going to ask that.
No, we tried, but no.
Yes.
But the calibration aperture of the infrared radiometer did sweep across Venus, but I don't think they found any phosphine with it. It wasn't designed to do that.
Yeah.
Okay, before we go to the questions, and I see we've still got no live questions. Julia, there's always things going on in planetary science. There's news stories breaking all the time. So what news would you like to share with us, Julia?
Yes, I found this recent paper that is by Martin et al. And this is about Enceladus. And I have a picture of Enceladus as well, so Saturn's moon. So Enceladus is having an ocean below the surface, we have the thick ice cover, we have an ocean below it, and there's also some activity going on in Enceladus, which is cryovolcanism, so that is usually when hot water comes out in a cold environment. And some of this activity can also be seen by these tiger stripes. You can see in the southern hemisphere of that picture, you can see these features that are called tiger stripes. And so plume activity is an important part of Enceladus geology. And these plumes also bring particles into the air. And once these cool down, you have a lot of ice particles that are on the surface of Enceladus. And so this study here looks at something which is called a pit chain. And if we go to the next picture, it actually shows a bit easier what that is. So the arrows actually indicate some of these pit chains. And they form when we have loose material that is above a fracture. And then when the fracture opens, because there comes heat from below, we have the loose material pretty much dropping into the void. And so we can have this kind of circular elliptical features. And these are very common in cold environments. For example, they also occur in Iceland, since we talked about this already. And in this study, they use a couple of methods to try and understand, like use the angles in these pit chains to measure the thickness of the regolith. And they come to the conclusion that at times regolith is about 700 meters, up to 700 meters, which is a lot of loose material you have on the surface.
Especially for a surface that has been resurfaced so recently. It's not been there for billions of years accumulating regolith because of meteorite bombardment.
Yes.
It's resurfacing itself by its plume activity. So that's a... Enceladus has plumes. Those of you studying S283, you'll be into chapter 4 by now if you're on time or just about to start it. You'll learn a lot about Europa and some about Enceladus. And Enceladus does have these active plumes, and it's clearly resurfacing itself somehow. But 700 meters of regolith.
Yeah, that seems to be a lot of plume activity in the relatively recent past.
Yeah,
so
that's a good find. So that's a paper in Icarus, so you can find that in the Open University Library if you want to. Who was it? Your lead author? Emily Martin. Okay, nice paper.
So do you have anything to share?
Yes, well, what I thought I'd share was the fact that Jupiter has now overtaken Saturn again in the stakes for a planet with the most moons. Scott Shepherd, who must have found more moons than anybody in the history of solar system exploration, has found a dozen more moons of Jupiter. So Jupiter's now got 92 moons.
Wow.
Got a couple of diagrams to show. So this is a view of the Jupiter system looking down from above. Now, there are 4 kind of pink circles near the middle. Those are the 4 Galilean moons, the big moons of Jupiter, Io, Europa, Ganymede and Callisto. Inside those, there's some inner moonlets, which don't even show at this scale. And everything outside is the irregular moons of Jupiter. And they've been coloured differently because they belong to different families. The red ones are all in retrograde orbits, and the ones in the other colours are in prograde orbits. So the prograde ones are going round anti-clockwise, and the retrograde ones are going round clockwise. And the next view shows the system side-on to show the situation a little more clearly. And that's how it looks. So the prograde ones are the red ones are all the retrograde ones, and the other colours are prograde ones. And so this confused me at first because Jupiter isn't in the middle of all of these. But what they've done is space these orbits out a little bit in a diagram, so you can see them separate from one another. Jupiter would be in the middle of all of these. So you've got to imagine these collapsed on top of each other. But the orientations are correct. If you just go, can we just go back to the previous slide? Sorry. So there's the green symbol, the green ellipse, I think, is the orbit of Valetudo, the retrograde, which is a prograde satellite orbiting in amongst the retrograde ones. It's not. So people think, oh, it's going to crash. But if you look go on to the next slide again, you can see that most of the time it's away from them and it's coming at it in different directions. So it's probably not going to crash.
It's safe.
In the short term, well, it's not safe indefinitely. Vale-Tudo does contain an element of, valediction and goodbye. It was given its name because one day it might well crash. And just to show these different families a little more clearly, the final diagram, the axes aren't very readable, but across the bottom is semi-major axis, and the vertical axis is the orbital inclination. So you see the red ones at the top are they all have inclinations greater than 90, they're retrograde. They're in 3 different families. And then the ones in the lower half of the diagram are all prograde orbits. Vale-Tudo was indeed the green orbit, and Carpo's the blue orbit. And there's several sharing similar orbits, which are prograde, which are the Himalaya group. And the Galilean moons plot right down at the bottom. They've got very low inclinations and relatively small semi-major axes. So families of Jupiter's moons, and all these outer ones are probably captured. Certainly the retrograde ones are captured bodies. And the fact that they're in families suggests that they may have come in as a single body, which then broke apart.
And some of them are so small that they don't even get a name, I guess.
These are all small. These are less than 10 kilometres.
Yeah.
And I think the International Astronomical Union has now decided that any moon that is smaller than a kilometre is going to get a number, but they're not going to bother naming it.
Okay. So we get lots of numbers.
Yeah. Well, Jupiter's moons were originally named after his lovers of all kinds of genders and species, and then his daughters. And I think they're running out of those as well now, so they're stopping naming things less than a kilometre. But of course, it's very difficult to measure the precise size of something that small. That's very hard to observe, so we're not quite sure what the size is anyway. So just before we leave this, I've got one more picture to show, which I took in Banbury on Wednesday last week. And I want to ask you how many moons are visible in that picture. So, in the chat, how many moons are in that picture? We'll give you a little while. I don't see any chat responses coming in. It's not going to affect your course outcomes. Oh, Andrew Ellison says 93. Murray Bray, okay, yeah. Well, okay, guys, well done. Oh, Ben says 1. Yeah. Okay, yeah, all right. In the middle is a crescent moon. That's our moon. The object below right of that is Venus, which has no moons.
No moons.
And the object above our moon is Jupiter, which has 92 moons. So, yeah, I think the correct answer is 93 moons in that view. So pat yourselves on the back, everybody who got that right. Of course, the moon has now moved away now, but Jupiter and Venus are getting closer and closer together. And in a couple of days' time, they're going to be less than a degree of arc apart. So if it's clear in the evening, pop out and have a look. They'll be quite spectacularly close. Okay, where are we now? We're going to answer some of your questions. Marco, we've had your question live. We'll get round to that. Thank you for that. We've had some in advance, which we'll deal with first. So on the moon's MOOC, Mark Jackson has asked, would it be true to say that there would be a higher chance of finding life on the moon than on a planet in our solar system? So that's one for you. Yeah. Astrobiology OU.
Thank you, Mark, for the question. Yes, apart from the planet that we all live on, I would say that currently Mercury and Venus don't look too habitable. We have maybe a bit of a chance on Mars, but we're still looking for life, so we still haven't found any. And then the outer planets are also not too great for life themselves, like the planets, but I would say that there might be some chances for some of the moons because they have an ocean and there is very likely some activity going on, hydrothermal activity that could be nutrients. It could be a setting of black smokers in the ocean on Earth. So we don't know what is below the ice. So yes, I would think that there may be a bit more of a chance to find life on an icy moon, maybe.
I would think so. And those of you studying S283, you'll be learning about possible life in icy moons in Chapter 4, when you finish learning about possible life on Mars in Chapter 3. But what we don't know is how simple it is to start life. The conditions are right to support life in these warm ocean floors inside Europa and Enceladus, but did life get started there? If you have to depend on life spreading from Earth to another planet, because we know life started on Earth, we can get life from Earth to Mars on meteorites blasted off Earth, but can we get life from Earth to the Jupiter system? Lots of unknowns.
Many unknowns.
Yeah.
But that's why we do science, right?
Yeah, that's why I said it'd be more important. If we find life on Mars, we won't know whether it started on Earth or not, at least take a while to work with that. If we find life in a moon of Saturn, that's almost certainly started independently of life on Earth, hasn't it?
I would agree.
If you can start life inside Enceladus, you can start life on an exoplanet just as easily. And there are more exoplanets than stars, so, and in fact more exomoons than exoplanets probably. So, galaxy teeming with life?
Probably.
Just microbes, or?
That's a good question. That is a very good question. But I mean, the chances would say that we are not alone, right? But yeah. Okay, so we have another question from the Moonsmug. Morak Lansendorf asks, I was fascinated to learn about the lava tunnels found on the moon and the suggestions these could be developed into underground bases for habitation. Is this just speculation at this time, or are there other plans afoot to make this a future reality? Dave, do you have anything to say to that?
Well, yes. The Artemis program is going to send people to the moon surface within 5 years. They're not going to be living inside lava tubes to start with, but in the longer term, they could be viable. But the problem with living on the moon is you're exposed to extremes of temperature, you're exposed to micrometeorites, which is not a big problem, but there's no atmosphere to shield you, and you're exposed to cosmic radiation. So you need to be inside a structure most of the time. Now you can build an igloo out of regolith or something, or you can go underground into caves. And there are natural caves on the moon in lava tubes. Let's have a look at the first picture, which is there's a scale bar there, 100-metre scale bar at the bottom left. That hole in the ground is about 80 metres across, and it's not a crater, it's far too deep. It's what they call a skylight. It's where the roof of a lava tube has collapsed. Now that surface is part of a lunar maria, formed by a vast flood of basaltic lava, and these basalt lava floods are very often fed by internal tube systems, and the field just inflates. And the tubes can then drain of lava towards the end of activity and leave you an underground tunnel. And they're very big on the moon. You can have 80-metre wide lava tubes because lunar gravity is only 1/6 of the Earth's gravity. Lava tubes on the Earth tend to be smaller. And I've got a picture of one in Hawaii here to show you. So there on the big island of Hawaii is a collapsed lava tube. Not such a nice round hole in the ground as we saw on the moon. But that guy in the distance is about to go down into that cave. We're looking along the length of the lava tube up towards the source of the lava tube on this particular Hawaiian volcano. And you could go down there and live in that cave on Hawaii if you wanted to, and you'd be protected from the scorching sun by day.
Isn't there some risk that they might collapse? At least on Earth there is, but...
Well, this lava tube is about 100 years old. It could well collapse in the next earthquake. The lava tubes on the moon have been there for at least 1 billion years without collapsing, so they're probably fairly safe. I've got about a minute of video which we'll play you now of a smaller lava tube I shot high up on Kilauea. So let's just have a look at that and see if you can hear what I'm saying above the noise of the wind. So let's play the video, please, Kate. OU Geological Society on the upper flanks of Mauna Loa. Here is a skylight. Hole in the ground. Now colonised by vegetation, was underground flow of lava. This big block here has been pushed up by when the flow was too much for the tube to cope with. the tube has since partly drained. That hole there in the centre is another skylight, at least 5 metres deep when I got to the brink of that. So, nice tube-fed flow coming down from Mauna Loa. It probably started somewhere up there, and I guess that knob in the middle is squeezed out from another overflow of the tube system. Okay, well, I hope you enjoyed that. Could you hear my feet scrunching on the fresh glassy crust of the lava there? I mean, you've got to be careful walking on young lavas. It's quite nasty stuff if you fall over. I was wearing thick gloves and not wearing shorts like many of my colleagues. Those were Open University Geological Society members on a trip to Hawaii that I took 4 years ago now, last year before COVID. Okay, so we're looking at for live questions. Marco Mori is saying I mentioned tectonic activity on Mercury, and he wants to know how that differs to plate tectonics. Plate tectonics is rather special to the Earth. It's because we've got a weaker asthenosphere, which is a zone in the upper part of the mantle that's directly below the lithosphere. That's the rigid very uppermost mantle and crust, which can slide around on the interior and is being created at ocean ridges and destroyed at subduction zones when one plate goes below another. Now, that's plate tectonics. Now, tectonics just means faults, and if the crust just breaks or moves sideways a little bit. And this is what's going on Mercury. Mercury, like most bodies, like all bodies that aren't being tidally heated, Mercury is cooling down over time, and silicates and indeed iron in the core will contract as temperature decreases, thermal contraction. So Mercury has lost about 7 kilometres in radius over the past 3 billion years. So it's contracting. Just think of an apple drying out and wrinkling. So the tectonics on Mercury is due to global shrinkage, and you get mostly thrust faults, where one terrain is thrust slightly over another. That's not like a subduction zone on Earth, where once it starts going, it keeps going indefinitely. So Mercury's tectonics is brittle fractures in the lithosphere, or if you prefer, in the crust, but it's not part of a pattern of global construction and destruction of crust. And Earth is the only planetary body with plate tectonics. Well, Venus. Tell us about Venus.
Yeah, Venus may have had some plate tectonics, but does not have now, or at least what we think of does not have now. Part of the Venus surface is very fresh, so it's volcanic and it's basaltic plains, and may have resurfaced in relatively recent geology, so maybe a billion years ago. Sorry, but there are parts of Venus that look a bit like what we think of continents on Earth. Mm-hmm. They are called tesserae. They are highlands, and they could have been older terrain that just got accumulated during some tectonic events, but it doesn't necessarily have to have been plate tectonics. So that is one of the things. We still don't really know what compositions they are. There has been speculation that they may be a bit more felsic, which usually means, at least on Earth, that there's more water present. But we still have to verify that. And there are upcoming Venus missions, so hopefully in about 10 years, we know a bit more about the compositions of the highlands and what exactly could have formed them.
Now, Andrew Ellison has just put a question.
Yes.
Recent results from Magellan suggest Venus's lithosphere is thinner in places. Did you know anything about this? Must be a recent interpretation of Magellan results, because Magellan
probably.
was 20 years ago.
Yeah, we still have to work with Magellan data there because, we don't have new data, unfortunately, and new missions are coming up in about 10 years.
But we don't know how Venus gets its heat out, do we? It must be producing much the same amount of radiogenic heat as the Earth.
Yes,
and Earth's
very
heat
likely.
Comes out by plate recycling mostly at a fairly continuous rate.
Yeah. So it may be volcanic activity. It may be something happening. So there's current research going on that looks at the alteration of the surface, and it can happen in this Venus atmosphere, can happen really quickly. So the question is, if you find unaltered basalts, this may actually imply that volcanic activity is much younger than we would have thought. So that is one thing. If the lithosphere is thinner, yeah, I have not read that research, so I'm not sure exactly what they based this on, but it could as well be thinner in certain places.
Yeah, okay.
Yep, okay. So there was also one more question in the moon.
Oh, no, that one.
In the moon smoke from Julian Livesey. He asks, I was reading about the current Capstone lunar orbiter. In the NASA overview, they say the moon's gravity is extraordinarily lumpy. So it's really hard to stay in orbit around the moon. What do they mean by lumpy?
Yeah, I had to look at what the Capstone orbiter is. And this is something which is orbiting the moon now in a very elongated orbit, which is to trial the orbit that the Lunar Gateway will take. The Gateway is the crewed station, the equivalent of the ISS, but around the moon, which will be a base for lunar exploration. And it's an orbit which takes about 2 weeks, and it's low some of the time, very short amount of time in each orbit, and a long way from the moon at other times. And there's all kinds of reasons of fuel conservation. Well, this is a great orbit to be in if you can stay there. And the NASA saying the moon's orbit is lumpy means, the moon's gravity rather, sorry Julian, the moon's gravity is lumpy, means that it varies spatially on quite a small scale. If we can have a look at the slide I got ready, this is the strength of lunar gravity mapped by the Grail mission. That was a pair of tandem satellites that were in the same orbit around the moon, only I think a few tens of kilometres apart, and they were measuring their distance from each other by laser interferometry, so they knew precisely how far apart they were. And when the one in front was approaching a region of locally high gravity, it would accelerate away and leave its companion behind for a bit. And as the distance expanded and contracted, they measured the strength of the gravity. And here you see how the lunar gravity varies across the globe. And if you can imagine being in a low orbit that comes within 1,500 kilometres of the surface, as the planned orbit will, that's smaller than the size of the moon. You can see that these variations in gravity are going to affect your orbit. So you've got to understand them to enable your orbit to work and not decay so quickly that you're going to crash. So this is a lumpy gravity field because the density of the near surface rocks varies on a fairly small spatial scale. I think that's what NASA meant by saying the orbit is lumpy. Any more live questions? I've got another one from Marco Mori. Where's the lower limit in size to be considered a moon? Yeah, there's always a discussion about this early on in the moon's MOOC, because in one of the videos, unscripted videos we recorded, somebody said anything smaller than a toaster is too small to be a moon, and some people said, "Do you mean a 4-slice toaster or a 2-slice toaster?" That's not an official classification at all, but clearly the chunks of ice in Saturn's moons, which are meter size, or the dust in Jupiter's, chunks of ice in Jupiter's, we can fix this in the edit, can't we, later on? The chunks of ice in Saturn's rings, which are meter sized, or the dust grains in Jupiter's rings, which are millimeter size, they're too small and too numerous to be seriously considered as individual moons. Yeah. But we have asteroids, which are 100 metres across, with 10-metre sized objects orbiting them. Those count as moons of the asteroids. Sure. But something 10 metres orbiting Jupiter, you wouldn't count as a moon, or would you? Certainly if it was part of a ring system, you wouldn't count the individual ring items.
Yeah, then Jupiter would have thousands of moons, right?
Yeah, but as we said earlier, anything orbiting Jupiter that is less than a kilometre is not going to get a name.
Yeah.
That's the IAU decision. They'll still give it a designation, and it will be regarded as a moon. Mm-hmm. but it's not going to be named. But the lower size limit to what is a moon, I think, depends on context. Because asteroid moons can be really tiny. But there was the
DART mission.
The DART mission went to Didymos and its moon Dimorphos, and Dimorphos was less than a kilometre in size.
It was pretty small.
Yeah.
I cannot recall exactly the size, but yeah, it was very small.
Okay, I don't see any more live questions. On the Moon's MOOC, Tanya Sluenhoek asked, are there plans to revise and update the Moon's course? Which means the Moon's MOOC. The Moon's MOOC we run on FutureLearn. It's in its 13th presentation now. I don't know if it will have any more because the OU no longer owns FutureLearn. We sold our share in it, but we're still offering courses on FutureLearn. But it continues as a badged open course on OpenLearn, but it's not supported by mentors, and there's no chat facility, so learners are on their own, they can't talk to each other. But we will be revising S283 in a small number of years, and we don't know whether this is going to be books like it currently is, or whether it will go entirely online, or what. I know some people prefer learning out of books, and others think books are a thing of the past and everything should be online. I mean, let us know what you think here. And we have had another live question now. Okay, Barbara Johnson, I'll put this one to you, Julia. Yeah. Does the discovery of more moons suggest that more have been captured over time, or is it simply due to more sophisticated equipment?
I would say it's just a more sophisticated equipment, the technology we have now to find much more. And also when we know where we are actually looking, like specifically, if we have the idea there could be more, then I think it's much easier to actually see. I mean, we have better telescopes, we have more on Earth-based better telescopes as well.
I would agree. That moons come and go. The Earth had a temporary moon a couple of years ago for a few orbits.
Yeah, true.
Yeah, we're just looking harder and seeing things better when we're looking at Jupiter's moons. And the campaign that Scott Shepherd ran that found these 12 extra moons, he wasn't actually looking for moons of Jupiter. He was looking for things in the Kuiper belt, but Jupiter came from the field of view. and they found all these extra moons for it.
So accidents.
Yeah. Oh, you can ask me that question.
Yeah, there's something still about the lumpy gravity. Is this the same for all bodies? So would similar maps of Earth, would a map of Earth look similar?
Yeah, thanks for that question, Martin. I think the moon's gravity is somewhat lumpier than the Earth. You may have seen most of those gravity anomalies on the moon were circular, and they're allied to craters. And people used to think the strong gravity concentric around lunar craters meant you got a very heavy meteorite buried under the crater, but now it's the lava that's infilled the crater, perhaps, or updoming of a mantle beneath big basins, lunar mascons.
That could, yeah.
Earth's gravity field does vary, but in a different kind of pattern. I don't think it's quite so difficult to orbit the Earth without gravity causing a major problem. This is interesting. I asked about what do you want, books or online, and 1, 2, 3, 4, 5 of you in a row have said you prefer books. That's interesting. Not a statistically valid sample, but interesting to know.
I agree, I prefer books.
Well, in default of any other questions, should we go on to talk about what Perseverance has been doing inside Jezero crater? Perseverance rover landed, it's
2 years ago.
2 years ago now, yeah. Mm-hmm. And it landed inside Jezero crater, which had smooth fractured crater floor unit, didn't it? And we didn't know if it was lake bed sediments or lavas, because there's a big delta coming into the crater. Let's have a look at this series of slides and see if that sparks people to ask questions. This is a colour-coded altimetry of Jezero crater. There's a scale bar there at the bottom. Jezero, I think it's 43 kilometres in diameter from memory. That fits about right. And you can probably see a channel snaking in at the western side of the crater, and another channel that's picked out in dark blue, low altitude, snaking away out of the eastern side of the crater. And so at some point in the past, probably 3 billion or so years ago, there was flowing water carrying sediment into the crater, and a delta built out into the crater. You can perhaps see the form of the delta there. You'll see it better in a little while. And there was a crater lake which drained out through that other channel. Let's take the altimetry away and start looking at the image mosaic. So the next slide, I think, is pretty much the same view, slightly bigger area. And we can zoom in with the next slide. Maybe Kate can point to the delta with her little cursor. There it is. Thank you. There's the delta sediments. And the lander is landed not far from where that edge of that delta is. So thanks. Let's go into the next view. Okay, even closer in. And I've got pictures of what's on the crater floor to show you when we get there. Let's go to the next slide. Okay, there's a geological map of the crater made before landing. The delta sediments are in blue, and the red area is the sort of fractured crater floor materials, which potentially were the sort of clays deposited in the lake that filled this crater, because the river channel came in from the left, deposited its sediment in that delta, and left clays on the floor. But Perseverance landed brilliantly in February or March 2 years ago, and had to trundle across some sand dunes to get to the good stuff, but found that all the stuff mapped in red here is lavas, and the orange stuff is possibly intrusive rocks below the lavas. Let's go to the next slide. Okay, this is a cross section of what's in on the crater floor. So a thing labelled Mars Formation, M-A-Z, is the lavas. The orange stuff is intrusive rocks, living cumulates. We don't know what's underneath that, but the original crater floor, and the delta that's on top of it is stuff in blue. You may remember seeing the blue stuff on the map, but the delta used to extend much further across the crater than it does now, and has been stripped away by erosion. So we've got on the floor, confirmed by Perseverance, basaltic lavas, more than one unit petrologically and morphologically, different kind of flow textures, which are not lake sediments, so not a great place to look for life, but have had water on top of them. You can tell that from the delta sediments, which have been deposited and then stripped away by some unknown process. What the hell got rid of the delta? But also there have been not hydrothermal reactions, but there's been some chemical interaction, yes, aqueous alteration of the lavas.
Yes.
So you've got water reacting with rock. You not think life could have got a toehold there on some kind of chemical energy?
I mean, from what the newest results are, it's very little water. It's just really small amounts that form just some alteration minerals, but it's not a lot. So the question is, how long was this water activity going on that actually was in contact with these rocks? But I mean, we know that there was a lake at some point. Yeah. The question is just, were these rocks in contact with that lake, or were some of the units that were above it in contact, and we don't see these units anymore? So these could have been altered much more and could have maybe potentially have recorded some life.
Yeah, there's been a lot of erosion in that crater.
Yes.
I don't understand. If you look at I haven't got pictures of the delta front, but you can find them on the internet. There's some boulders as big as
huge.
Yeah, huge boulders. Boulders the size of a large boulder. size of a Mini, size of a double-decker bus. So, well, maybe not, but pretty damn big, which are there in some of the delta sediments. And how can you strip those away? Or were they friable? Did they just break apart to dust, which the wind could blow away?
Maybe part of it is the environment. So if you have some water and then freezing conditions, you maybe just make the rocks brittle and much more easily transportable over time. The question is then, why is that other part of the delta still there?
Yeah. Well, the question from Ben: how confident are we that water was for liquid transporting the sediment for deltas? Couldn't it be liquid carbon dioxide? Normally it's sublime straight from ice to vapor, doesn't it? What conditions do you need to get liquid?
I'm not sure if liquid CO2 would have been stable for long on. To look up.
There's a phase diagram in chapter 3. It doesn't work to have.
Yeah, I'm relatively sure that
it has to be. Water's the only viable fluid. Carbon dioxide won't be liquid under feasible conditions, and I think the phase diagram is in book 1, not in book 2.
Okay. No, but I would also agree with that CO2 is very likely not in a fluid state on Mars, or would have been in a fluid state on Mars. So the most likely liquid that we have is water. And especially these huge amounts that we would have to form this delta, and also to form other features like Valles Marineris on Mars that need a lot of we assume water. Yeah. It's most likely.
Okay, well, I see no more questions coming in, so I'm going to ask you one about, we've got 3 Venus missions coming up. I know Venus is maybe your favourite planet. Don't want to put words into your mouth, but what other good things are going to come out of Envision and the other Venus missions?
Yes, so they all are going to be a little bit different. One of the exciting ones is Da Vinci, because it is going to measure the atmospheric composition, and it's also having a descending probe. So it's actually going to measure the composition of the atmosphere and also taking pictures of one of the highlands, so the tesserae of Venus. It doesn't have other measurements on it, like the probe itself, but at least we will get hopefully some images. So that is very exciting, and would actually improve our knowledge of, well, actually get a close-up of these rocks, and maybe we can see a bit more what they're composed of.
Will Da Vinci operate on the surface?
Da Vinci is an orbiter, and then it will have one descending probe, and it will send through all of the atmosphere, take measurements while it's doing that, and then at some point it will die because nothing survives on Venus.
Is it intended to still be working when it gets to the ground, or is it expected to die?
Hopefully. So
okay,
hopefully it will actually function until it actually lands, and then. Yeah, because temperatures are 470 degrees, it's 90 bars, there is a CO2-rich atmosphere, it's about 96% CO2, and then a little bit of SO2, some not so pleasant
right, so that's Da Vinci.
gases. That's Da Vinci. And then Veritas is the other NASA mission. That is a orbiter only, but it does a lot of radar measurements of the composition of the surface. And that would be very helpful to understand a bit better what kind of materials are there in the tesserae. Do we actually have some other minerals there? What alteration minerals could have formed? And Envision is doing a similar thing to Veritas, but is looking much more specifically at certain areas that are out of interest. So initially it was planned that Veritas would be there first and Vision could use that data, but we got a slight delay. So Veritas is probably going to be there at the same time, unfortunately.
And Envision is the ESA?
Envision is the ESA mission, yes. So they have one of the issues with Venus is that it has a very thick atmosphere, so we have to rely on mostly radiometric data, anything that actually just can see through all of this thick cloud cover. So it's not as easy as Mars, where we have these nice images from orbit.
Okay. I think it's time to call this to a halt. So I was just going to look at the widgets before we finished. Perhaps we can bring them up on screen one at a time, can we, Kate? What are you studying? Okay. Mostly S283. We've got half people on S283 and nobody posted a question in advance on the S283 forum. Interesting. A third of you not studying at all, and 14% on the moon smoke. Thank you for that information. That's nice to know. Can we keep going through the widgets, Kate? So this is favourite moon of Jupiter, I think. Okay, nobody likes poor old Ganymede. And Europa, well, yeah, I mean, Europa, it's a no-brainer, really, I think. Yeah. Julia is nodding, everybody. And so am I, internally. And what about favourite moons of Saturn? Oh, almost a tie between Enceladus and Titan. Titan is a moon that 283 students will learn about in Chapter 5 of Introduction to Astrobiology. That's the one with lakes of liquid hydrocarbons.
Titan is very intriguing, and I'm really looking forward to the Dragonfly mission.
Yeah, drone. How many wings has it got?
I'm not sure about the technical details, but it's going to be a flying object, so it will not be a rover, but it will be pretty much a little helicopter flying from one area to another, so that it can move around and it can study these areas a bit better.
It's going to a dune area.
Yes.
Sadly not a lake shore.
Sadly not a lake, but
it'll still be good.
It'll still be nice.
And the final widget is, which is more likely to have life? I think you've swayed them, Julian, or did they know that already? Thank you, everybody, for taking part. We will run another of these for S283 around about November time next year, and we'll try to make sure that everybody who needs to know, who wants to know, finds out. Julia, thank you for giving up your evening.
It was a pleasure,
working
thank
with you. And Kate and Ben in the back room, thank you for your help, and good night, everybody.
Bye.